Alright, welcome. In this video, I'm going to be proving the ratio test. So, remember the ratio test says if we're looking at an infinite series, the sum from 1 to infinity of a sub n, and we've got a limit of the absolute value of the ratio of successive terms coming back L, and that limit is less than 1, then the series converges absolutely. If that limit is greater than 1, the series diverges. Okay, if the limit equals 1, then the test is inconclusive, but I'm not really getting into that here. Alright, so first I'm going to prove the forward direction, or the converges part. Right? So I'm just going to suppose that that limit L is less than 1. And then I'm also going to let R be this number that's between L and positive 1, which if L is less than 1, then there has to be a number R, a bunch of numbers R to choose from, between L and 1 in that open interval. Okay, we know that the limit as n approaches infinity of the absolute value of the ratio an plus 1 to an is equal to L, which is less than R. Okay. And that means that for all n beyond some threshold, we will have that absolute value being less than R. Okay? As close to L as we want does mean that we're going to have to go underneath R. Okay, and that will mean that, if I was to just look at the absolute value of the ratios, the ratio of the absolute values, and then multiply both sides by the absolute value of a sub n, I'd have the absolute value of a sub n plus 1 less than the absolute value of a sub n times R any time that n is beyond this capital M letter. And, so if I was to actually, I think this will help maybe for the visualization, to actually replace n with m and m plus 1. And now I'm going to consider what would happen if I thought about a sub m plus 2. Okay. If I did that, well, I could just say, well, that kind of the same principle is going to apply. That's going to be less than a sub m plus 1 times r. Okay. But I just wrote down that a sub m plus 1 is less than a sub m times r, so that would mean that a sub m plus 2 is, transitively less than the absolute value of a sub m times 2 powers of r. And if we were to generalize this, we'll have a sub m plus k's absolute value being less than the absolute value of a sub m times r to the kth power anytime k is greater than or equal to 1. And so what we're going to do is we're going to really think about, comparing this to a geometric series. Okay, t, I'm just going to make up sum t, is going to be the sum from 1 to infinity of the absolute value of a sub m times r to the k. Now that's going to be a geometric series. It's going to converge by the geometric series test because I decided that r was some number between L and 1, right? R is definitely less than 1 in absolute value. And now I'm going to think, well, but the terms of my absolute value AK series were even less than that, right? So this is going to converge by direct comparison, the series that I've written in red. And that means that that series, without the absolute values, is going to converge absolutely. And so we're really close, okay? We have the sum from k equals m plus 1 up to infinity, where m is just that threshold beyond which we get underneath r. Okay, so if I'm interested in the original S series that's written in blue, the sum from 1 to infinity of a sub n, okay, I'm missing some of the terms, but the number of terms that I'm missing is finite. So I'm going to add on a finite number of terms to this absolutely convergent series, and I'm going to have an absolutely convergent series. Now, for the second part, I think this is going to be a little easier. We're going to let L be some number that's greater than 1. Okay, and we know that the limit of the absolute value of the ratio an plus 1 to an, that's going to be L, which is a number that's bigger than 1. Now, if that limit is true, then that means that the ratio, the thing that we're taking the limit of, has to be bigger than 1 for all n beyond some threshold, just like the other one. That's the definition of a limit as n approaches infinity. Okay, and now what I'm going to do is kind of just say, well, it's beyond that m, I'm going to have this inequality for sure true. And again, I'm going to look at it just the same as the other one. I'm going to eventually think of this as the ratio of two absolute values and then multiply both sides by the absolute value of the denominator. But I'm going to write a sub m plus 1 over a sub m's absolute value is greater than 1 but also a sub m plus 2 divided by a sub m plus 1's absolute value is greater than 1. Because I really want to convince you of why this is true in maybe a better way than I did on the last one. The last one was kind of had a lot going on, trying to fit it all on screen. Okay, here, I'm going to look at these as the ratio of two absolute values on the left-hand side and then multiply them across and say, all right, on the first inequality, I'll have a sub m plus 1's absolute value greater than the absolute value of a sub m. And then for the second inequality, I'll do the same thing, and I'll have the absolute value of a sub m plus 2 greater than the absolute value of a sub m plus 1. And if I was to kind of combine all these things together and recognize, hey, I'm taking the absolute value of these numbers that might be positive, might be negative, but are probably not going to be 0, I'm going to have, okay, the a sub m plus 2 is greater than absolute value of a sub m plus 1, which was the inequality on the right. But I could also, bring in something else and say that's actually even greater than the absolute value of a sub m, which is going to be a positive number because it's the absolute value of a term in an infinite series, which I would hope is not 0. And so we can see that the actual size of these a sub m's beyond this threshold is increasing, which means that it cannot be going to 0, right? This limit cannot be 0. The limit of the terms is non-zero. It might not be infinity or negative infinity, but it definitely can't be 0 if the absolute value of these things is increasing. And if the limit of the terms is not 0, the series doesn't even have a chance to converge. So we're going to say by the divergence test, S will diverge. Or it's sometimes called the nth term test for divergence. Okay, so that's the ratio test. That's why it works. As you can see, it's not terribly illuminating kind of probably your intuition about it. Okay, well, if it's the ratio comes back less than 1, it's kind of like a geometric series, and if it's greater than 1, well, the divergence test would take care of it. That's exactly how we proved it, and these were the details. So that's going to be all for this video. Thanks for watching.